So there was one main thing that we did last time. Okay, we were basically doing something like the method of least squares, but for the inner product space. Okay. So, increase the percentage. Consider like, whoops.
Okay. Can't check out the ceiling.
Okay, so let me try and review the main thing that happened last time. Okay, so last time we had this theorem. It said the following. So you have an inner product space. You have an inner product space, and then you have a subspace. Okay. Inner product space. You have a subspace inside of it, right? And you have V1 through Vn. Let's call it Vk because we've been using a k elsewhere. An orthonormal basis of S. Okay. So just to review what we did last time, right? You have an inner product space, you have a subspace, and you have an orthonormal basis of the subspace. Okay, you don't have a basis of the whole space. You just have an orthonormal basis of that subspace. Okay, and then you have some b in the space. Okay, so the picture you have in Euclidean space is like this, right? You have your subspace, right? That subspace is sitting inside of your Euclidean space, and you have some b here. Okay, and you're wondering what's the closest vector in S to B. Okay, and this is how we're gonna get it. There's a nice way. This is basically a nice way of getting the closest vector. Okay, nice way of getting the closest vector. Okay, if you have an orthonormal basis, right? If you have an orthonormal basis, closest vector in a subspace. If you have an orthonormal basis of that subspace. Okay. Okay. So. There's a student from the other section. Let's welcome him. Okay, so right. So you have some vector in your space, and you're looking for the closest vector in the subspace. Okay, and what was the way of getting it? Then what turned out to be the closest vector? Does anybody remember? How did we get that closest vector? How do we get that closest vector in the subspace? If we let P denote some vector, right? Anybody remember? You use the orthonormal basis, okay? And what you do is you say, well, I'm going to take U1, and I'm going to take the inner product of B against U1, and then use that much of that amount of U1, and I'm going to do that for every element in the orthonormal basis. Okay, that's going to give me something in S, right? Because we're taking these things that are in S. Okay, we don't get something. I mean, it's in V, but it's inside of S. Okay. If we let P be this, then this guy P is the closest vector in S to B, right? P minus B is perpendicular to S. Okay, this is the main thing that we did last time. Okay, just to try to clarify last class. Okay. Okay. Now here's the picture, right, in Euclidean space. But remember, there is no picture, right? We're actually in an inner product space, an abstract inner product space. So, right. So in fact, there's another picture. It's an oral picture, actually. So it's an oral picture. You have this, you can think of this B as a sound, okay? This B is the sound of my voice, okay? This B is the sound of my voice, right? It's, over a certain period of time. Okay, so you have some period of time, and you have the sound of my voice. Okay, that's what B is. And you're wondering, how do I, what's the closest thing in the subspace that consists of the span of a bunch of waves. Up to, I don't know, like cosine, 1000x, say. Sine 1000x. Okay. Okay. We saw that this is actually an orthonormal basis. Right? An orthonormal basis of S. Okay. With respect to that inner product that we created on negative pi pi. Okay? And so what this is saying is that if we create this sound, right? If we create a sound by taking my voice and taking the inner product of my voice against these functions and adding up those combinations of these functions, that is the closest sound to my actual voice. That is the closest sound to, whatever recording you have of my voice. Okay? The closest with respect to the sense of distance you have in this vector space, right? So the vector space is continuous functions on some time interval, right? And you have an inner product. Remember, meaning you integrate one function against the other function. Okay. So this is just as good and maybe even a better way of thinking about what this theorem means. Okay, because this is more abstract, and this sort of frees you of thinking that we're stuck in Euclidean space somehow. Okay. Okay. So this is picture 1. This is picture. Really picture 2. Right. You think of it in terms of sounds. Okay. Okay. So that was the main thing that we did in the last class. This theorem is going to give us the answer to a particular problem. The problem is, what if we don't have an orthonormal basis? Right? What if we don't have an orthonormal basis? Right? Well, we want to have an orthonormal. You can see that it's good to have an orthonormal basis, right? But now we suppose you don't have one. There's a way of constructing one. So there's a construction method. Called Gram-Schmidt Orthogonalization. Gram-Schmidt orthogonalization. Okay. Basically, how to make an orthonormal basis from a basis. Okay, so somebody gives you a basis, and then you want to construct the orthonormal basis out of it. Okay. I saw a movie on an airplane recently, airplane ride, Hidden Figures. I don't know if you've seen this movie, right? Hidden Figures about Catherine, what's the last name? Johnson, Catherine Johnson, thank you. A woman who worked for NASA in, I forget. Anyway, she worked for NASA at the time of the first launch to the moon. They mentioned Gram-Schmidt orthogonalization. When she first enters the job, they say, "Can you do Gram-Schmidt orthogonalization?" And she's like, "Of course." Or I think they asked her, "Did you use Gram-Schmidt orthogonalization?" And she said, "Oh, why wouldn't I?" Or something like that. Anyway, so let me state the construction. Okay, so here's the theorem. So you have V and inner product space, B a basis. Okay, and then you want to construct an orthogonal basis. We can construct an orthogonal. I'm sorry, an orthonormal basis recursively. An orthonormal basis U1 through UN recursively as the first thing we do, sort of obvious, we take, we want an orthonormal basis, so we take our first element and we divide it by its norm. Right? That's sort of like the obvious move to make. Right? We want an orthonormal basis. We want everything to be norm 1. So we take the first vector and we take the first basis vector and divide it by its norm. That's a good beginning. Okay. Then we define, so for k greater than or equal to 2, we let u k plus 1 be b k plus 1 minus summation b k plus 1 uj uj as j goes from 1 to k over the norm of that. Okay. Okay. Can anybody see the idea here? Can anybody see the idea here? You're taking b k plus 1. You're creating a vector, right? I'll stop for a second. Oh, hold on for a second. People are still pumping. Can anyone see the idea? I mean, dividing by the norm on the bottom, that's just to ensure that this thing is norm 1, right? That's sort of obvious. You don't have to worry about this bottom part, right? We do that because we want an orthonormal basis, right? Okay, well, let's look at the top. What's the meaning of the top? b k plus 1 minus this thing here. Well, what's this thing? What is this thing? Anybody recognize it? This is exactly the thing from over there. That's P, right? This is P from the theorem. Right? This is P from the theorem where we're taking our bk plus 1, right? And we're getting the projection P, and we're subtracting that thing off, right? What is S? What is the S here? What is the S here? Right? What's S going to be? Well, it's a thing with orthonormal basis U1 through UK. Right? S here, right? So we create this this thing, like what's the idea? What's the idea? We get P in S, where S is the span of U1 through UK. Right? To get UK plus 1, we get P in S, where S is the span from U1 to UK. Then B minus P is in S perp by the theorem. Right? P minus B or B minus P, it doesn't matter, is going to be an S perp, right? And so B minus P over B minus P is, we take that as our UK plus 1. Then you let UK plus 1, UK plus 1 be this guy, right? So that guy will be perpendicular to all the other guys, and it'll be norm 1, right? And so that's what we want as our next element of the orthonormal basis, right? We want somebody who's perpendicular to all the other members of the orthonormal basis and is of norm 1. Right? And so that's the right candidate for it. Okay. Okay. Let me sort of sketch the idea more graphically. So, right, somebody gives you a bunch of vectors, B1, B2, B3. Okay, somebody gives you a bunch of vectors and says, could you make an orthonormal basis out of this? Okay, and so make an orthonormal basis out of this. Well, the first thing you're going to do is say, well, let's take U1 to be B1 over its norm. Right? We just take B1 and we shrink it down to norm 1. That's going to be our U1. Okay. That's, again, we said that's the obvious first move. Right? Now, for U2, right, what are we going to do? Well, we're going to take B2, right, and we're going to subtract off the projection of B2 onto U1, the U1 subspace. Right? Right? We've got the U1 subspace right here, right? This is the U1, the subspace spanned by U1. A subspace spanned by U1, and we say, okay, well, we want something perpendicular to that guy, so let's take the projection. Let's take the projection. That is this B2 U1, whoops, U1, right? That's projection P. And we take B2 minus that, B2 minus that is going to be perpendicular. Right? This is B2 here. This is B2 minus the projection. Right? And by the theorem that we just said, that's going to be perpendicular. Right? So, but we also want that to be norm 1, so let's divide it by its norm. Right? And then U3, you say, okay, well, I've got my U1 and U2 now. Right? So you get this thing, something perpendicular. Right? You get the U2 is something perpendicular to U1, right? And you say, okay, now I want my U3. Well, I'm going to take my B3, and right, these guys are a basis, so B1, B2, B3 are linearly independent. Right, because they're a basis. We take U3 and we say, okay, we want B3 we want to chop off the part that is, we project onto the span of U1 and U2, right? We get the span of U1 and U2, that's something like this, and then we project down to it, we get something perpendicular to that, right? So we say, okay, let's subtract off, B3's projection onto the U1, U2, onto the U1, U2 plane. Okay, and then divide by the norm, and we keep on going. Okay, and so that's the Gram-Schmidt orthogonalization process. Okay, that's all I want to say about it. If you want it, there's a little bit of detail that I'm skipping over, but it's not difficult if you want to read it. Okay, does that make sense? Anybody have questions about that? Okay, so any questions? We are going to need that once we get to the last topic of this term, singular value decomposition, if we get there. I'm not even sure if we get there. Yeah, the last topic is sort of the greatest and the hardest thing. Then we'll make it. Let's see. Okay, so let's. Okay, so there's a couple more sections in this chapter, but I'm going to skip them because I do want to get to this great application at the end. I'm hoping to. Okay, so let's go on into chapter 6. So chapter 6, 6.1, eigenvectors and eigenvalues. And remember that I said that this was sort of it would have made a lot of sense to go from chapter 4 into chapter 6, skipping this inner product stuff. But in fact, we need the Gram-Schmidt orthogonalization in 6.5. So maybe it does. There's something to be said about doing that first as well. Doing that as well. Okay, so let's get to it. So you have a square matrix, okay? Back in the world of square matrices. But now we have complex numbers. Okay, so this denotes the complex numbers, right? Just like the R with a slash through it denotes the real numbers. Okay. But our matrix is just real for now. Okay, our matrix consists only of real numbers. If there exists a vector v non-zero such that a times the vector equals lambda times the vector, we say that lambda is an eigenvalue of A, and that V is an eigenvector of A with eigenvalue lambda. Okay, so So we've seen this sort of thing before, remember? Right? More than once we've said that it'd be a good thing if we could have a basis that consisted of eigenvectors, consisted of vectors that when you hit them with the matrix, they only get multiplied by a number. Okay. So distantly, you remember, in chapter 4, this was a good thing a few times. Okay. Okay. So now we're going to formalize everything. Okay. So exercise 1. Let lambda be an eigenvalue. An eigenvalue of A, and let E sub lambda denote the set of all eigenvectors of A with eigenvalue lambda. And I tend to abbreviate eigen as just an E. So if I write E vectors or eval, I mean eigenvectors and eigenvalue. Sorry, it's not that good an abbreviation. Okay. Show E sub lambda is a subspace. Okay, so that's an exercise. See if you can think about it for 1 minute and see if you can come up with something. Why is it true that if you have a bunch of eigenvectors, well, for the same eigenvalue, then they form a subspace, if you look at all the eigenvalues, vectors for that eigenvalue? So you have to remember, what's a subspace? How do you show something's a subspace?
That it's spanning and linearly independent.
You're thinking of the word of the definition of basis?
Scalar multiplication and addition.
That's right. That you can add guys together and you can multiply them and not leave the space. Okay. So that's okay, don't worry. Okay, so is it true, right? Is it true that, let's say that V1 and V2 are in this thing? Is it true that V1 plus V2 is in there? Second part, right? Say that V1 is in the space and alpha is some number. Is it true that that alpha v1 lies in the space? Lies in that set? And the answer is sure, right? Right? Because this first part, what we're saying is that, say that AV1 equals lambda v1, and that AV2 equals lambda v2. Does AV1 plus v2 equal lambda v1 plus v2? Right? And of course that's true, right? By linearity, right? When you're multiplying A times v1 plus v2, that's AV1 plus AV2. So that's the end of that, right? And then the second part is saying that, right, if A v1 equals lambda v1, does A alpha v1 equal alpha equal lambda alpha v1, right? And of course, again, that's true. Okay, So the set of all eigenvectors forms a space, a subspace. We call this thing, we call A sub lambda an eigenspace. Okay. The collection of all eigenvectors corresponding to a particular eigenvalue is called an eigenspace. Okay. There's another way of, so I have a 1 here. Why do I have a 1 here? It's because there's a 2. And 2 is a different way of thinking about this. So this is what I have in my notes as dull. And I have slick in over here. Okay. This is mainly, I think, because the graduate student who was a TA for my first year of math in college used these terms. He would say, oh, this is a really slick proof. This is a really slick proof. It seems really, I guess it sounds very old-fashioned, right? To call something slick. but I still use these terms. Okay, so okay, so think. Look, here's the slick proof. If you have an eigenvector, well, what does that mean? That means that AV equals lambda V, right? Of course. That's the same thing as saying that AV equals lambda IV. Right? I'm going to throw in the identity matrix here. Of course, it doesn't do anything. Okay. That's the same thing as saying that A minus lambda I V equals 0, the 0 vector. Right? I move these guys to the left side, and then I distribute the V out. Right? Okay. But what's that saying? That's saying that V is in the null space of A minus lambda I. Right? Right? You are an eigenvector if and only if you are killed by A minus lambda I. Right? You're an eigenvector with eigenvalue lambda if and only if you're killed by the A minus lambda I matrix. Okay? So in other words, right, A sub lambda is the null space of A minus lambda I, and of course it's a subspace. It's a null space, right? Okay. Okay, so that's actually a better way of thinking about why the eigenspace is a subspace. Okay. Exercise 2, show that lambda is an eigenvalue of A if and only if the determinant of A minus lambda I equals 0. Okay. Now think about why that's obvious. Why is it obvious that lambda is going to be an eigenvalue if and only if the determinant of A minus lambda I equals 0? Why does it seem reasonable? Talk with somebody nearby about, Lizzie, talk with Eric, please. Talk with somebody nearby about the relation, why these things ought to be related.
then couldn't give eigenvalue the only vector. Is it almost in line from that 0? The only vectors are eigenvector and 0. And lambda is like lambda 0.
Okay, anybody wanna say something? Why are these things related? What is the determinant of, what does it mean if this thing is 0? The determinant of this is 0. What does that tell you? You know a lot. Yeah, determinant of a matrix is 0, so it's singular, right? It's non-invertible. In other words, what other things you can say? The null space, something like the null space. Null space is non-zero, right? So, right, the point is that, right, the determinant of A minus lambda I is 0 if and only if A minus lambda I equals 0, B equals 0 has a non-trivial solution. Right? But that's the same thing as saying that lambda, E sub lambda contains something. Right? That would mean that E sub lambda is not 0. Okay. In other words, you have an eigenspace. Right? That's the same thing as saying that there's some vector such that A, B equals lambda B. Right? So, right, if lambda is an eigenvalue, then the determinant of this thing is 0. If the determinant of this thing is 0, then lambda has an eigenvalue with eigenvalue lambda. I'm sorry, then A has an eigenvalue with eigenvector with eigenvalue lambda. I stayed up too late. Okay, make sense? Make sense? Anybody confused? Okay, so the above. So the above gives us a way to find eigenvalues and eigenvectors. So we introduce the following definition. We say suppose you have a matrix, and we think of let lambda denote a variable. Okay, we think of lambda as a variable. Okay, then we call the determinant of A minus lambda I the characteristic polynomial. Characteristic polynomial of A. Notice that its roots are the eigenvalues of A. Right? We make a polynomial and we say, well, whenever this polynomial, whatever lambda makes this polynomial equal to 0, well, we know that those guys are going to be the eigenvalues. The roots of the polynomial, whatever lambdas make that thing equal to 0, those will be, you see that those guys are the eigenvalues. right, by this thing here. Okay, so here's an example. Make this concrete. A is 6, -4, 3, -1. And then you get the characteristic polynomial, the determinant of A minus lambda I. Well, that's the determinant of A minus lambda I. Right? The determinant of A minus lambda I, right? Lambda I is, of course, the matrix lambda 0, 0, lambda. Right? So you subtract that guy from this guy, you get this thing, you take its determinant, right? It turns out to be, if you work it out, lambda squared minus 5 lambda plus 6. And so you get lambda minus 2, lambda minus 3 is the characteristic polynomial, right? And so, so we know that A has eigenvalues. Eigenvalues 2 and 3. Okay, so it's like you get to use your your junior high school knowledge in this class. Okay, okay, so great, right? You've got the eigenvalues, but now that you have the eigenvalues, so you know that E sub 2 and E sub 3 are the eigenspaces, right? You know, E sub 2 and E sub 3 are the eigenspaces, and we can figure out what they are, right? What are they? Right? Let's work it out, right? E2, remember, E2 is the null space of A minus 2I. Right? The null space of A minus 2I. So you say, okay, well, let's look at A minus 2. A minus 2I is the matrix 4, -4, 3, -3. Right? And you can calculate the null space, right? 4, -4, 3, -3, 0, 0. Right? Calculate null space. Right? You just do, what we did many times before. You do your reduction. You see what's going to happen, right? These things are dependent. The second one is going to vanish, right? And the first one we can divide by 4 without changing the solution set. Right? And so we see that x equals y, right? That E2 is the span of 1, 1. Right? Similarly, we see that E3 is the null space of the matrix minus 3, right? So it's going to be 3, -4, 3, -4, right? Which is equivalent to 1, -4/3, 0, 0. Right? And so we see that this is the span it has as its basis, right? 4/3, 1. Okay, and so you see this is actually really great, right? We get we have 1, 1. 4/3 one is a basis of R2 of eigenvectors of A. Right? So for example, if we took this thing and looked at its matrix representation, we made its matrix representation, we get, what do we get down here? So I'll let you think about that. What is a prime? It's not an exercise, it's a review. Does anyone know what it's going to be? Just offhand? Can anyone calculate really fast? Not that fast? Actually, there's no calculation involved. Okay, I'll let you think about it. Let me finish us with a couple of observations. So, some simple observations. Say A is a real matrix, right? It's in R n cross n. And lambda, a complex number, is an eigenvalue. So, I don't know how many of you have heard of this thing called the complex conjugate. Complex conjugate? Anybody heard of it? Okay. If you have a complex number, a plus bi, like 4 plus 3i. So, here it is. You have a complex number, then a minus bi is called the complex conjugate. And it's written lambda bar, the complex conjugate. Of lambda. Then, so claim, then lambda bar is also an eigenvalue of A. So those of you who've seen the complex conjugate before, where have you seen it? Where have you seen it? Maybe you've seen it when you're doing quadratic equations or something, right? You have, you know that if you have a complex root, then the complex conjugate is also a root, right? Complex conjugate is also going to be a root, and this is basically that thing, right? Because what's the point? The point is that lambda is a root of this real polynomial, right? And the roots are going to occur in complex conjugate pairs, and so if lambda is a root, then lambda bar is also going to be a root. Okay, actually, let me not talk about this right now. I think Sorry, we'll start off with this next time. We'll start with this next time.